So I invite Shri Mukesh Singhal, former CMD in charge of NBCIL. He passed his engineering, chemical engineering from IIT Roorkee. I don't want to spend more time on introduction. He is well known. So I request Mukesh ji to start his talk. And I request him that he let him finish in 45 minutes.
My topic of presentation, Indian nuclear power program, journey so far. Now, after two good presentations, overall summary has been conveyed by our CMD and PCL, and now Grover Saab has conveyed the Santi Act. So things which we are doing has come in a transparent manner. So by doing that, all that things, how we have proceeded to this journey, I will be covering that part. Yeah, next please. So table of contents, importance of nuclear energy in India, guiding principle of Indian nuclear program, evolution of nuclear power plants, evolution of nuclear safety, importance of R&D in nuclear energy, tariff and project cost across reactors. Next please. Next please. Yeah. So it as brought out in the beginning itself, India being the most populous country of about 1.46 billion population with GDP growth rate of 6 to 8% needs large energy expansion plan. Correlation exists between Human Development Index and per capita energy consumption. At present, at the end of 2025, we have the per capita energy consumption around 1460 kilowatt hour per year. And if we see 14 years back in 2011, it was 700. In 14 years, our consumption has become doubled. Now, if we see a dividing line exists between per capita electricity consumption between developing and developed country, around 4,000 is the cutoff line. So if we have to reach to Viksit Bharat by 2047, so consumption will be around 4,000, so will be again 3 times from the 1460 to around 4,000 in 22 years. So this sets that consumption will increase by 3 times, and if we consider the population increase, industrialization, so it will be much more. And we have seen today electricity installed capacity is 500 and projected, as told in the previous speaker, 1800. So it is more than 3 times. Next slide, please. Nuclear energy is the green energy of choice. So as we have seen, to meet the energy demand, all resources need to be explored to their full capacity. But climate change arising out of greenhouse gas is among the most important challenge facing world today. As we know, and we are seeing different calamities all over the world. So India is committed to have net zero target by 2070. Under this, the first assignment is to have first target on which this theme is there, 100 gigawatt nuclear power by 2047. Life cycle emission from mining of ore to waste disposal of nuclear power are very low, as like 2.5 to 5.7, around 4 gram carbon equivalent per unit, versus around 200 to 350 for the coal and 150 for the gas plants. So baseline CO2 emission in India from predominant technology coal are around 1 kg per unit. So thus, every unit of nuclear power generated saves 1 kg of CO2 emission. Nuclear power is benign, and life cycle greenhouse gas emission of nuclear power is comparable to solar and wind. Next, please. Guiding principle. If we see, actually for developed countries, this while doing their military studies, strategic studies, actually nuclear came like as a spin-off technology for them. But in India, it was well structured. And in the beginning, 1944, Dr. Homi Jahangir Bhabha, the father of Indian nuclear program, addressed a letter to Sir Dorabji Tata Trust, outlining the urgent need to initiate nuclear research in India to keep abreast with international developments. And it was finally approved, and Tata Institute of Fundamental Research was set up, and all beginning studies, research, cosmic rays, electronics equipment, various type of studies were initiated in that one. Subsequently, in 1948, Atomic Energy Commission was constituted, And exploration of availability of raw material resources in the country was the major task. So various studies were performed and it was seen what is available in the country so that we can decide our power plan. Next please. It became very clear that we have a limited uranium but vast thorium resources. So Dr. Bhabha conceived a 3-stage nuclear program to have optimal exploitation of the resources and best utilization in the industry. Like nuclear industry at that level were premature, so vessel like Calandria vessel or this type of things can be considered, and optimization of resources. So he framed a 3-stage program. So under first stage, natural uranium, which is constituting 0.7% only fissile material, and uranium-238 99.3 is to be used as a fuel in the first stage, which is a horizontal Calandria based model. Pressure tubes are horizontal. It will produce the available resources at that time 12 gigawatt energy for 30 years. So this is the limitation that time. But in this one, the used fuel will come out as spent fuel in pressurized heavy water reactor, where moderator will be acting as heavy water. So therefore moderator is required. So lot of things came out what is required, and we will come subsequent to that. Spent fuel is to be reprocessed, and so therefore closed fuel cycle is required. In that closed fuel cycle, plutonium and depleted uranium was isolated, which will act as a fuel for the next stage. So this is a 3-stage. So electricity will produce and the fuel will become a part for the next stage. The first stage is the PHWR, which is the main stage of our power program. In second stage, the plutonium which have generated from the first stage, which is small quantity, and then depleted uranium which contains large U-238 unutilized. So this is much larger. So this will go in the fast breeder reactor. And breeder is a reactor where whatever fuel it is consumed, it will generate more fuel than the. So therefore it becomes a self-sustaining. So plutonium will recycled and it will generate energy for 300 gigawatt energy for 30 years. And basically all plutonium generated in the first step and with depleted uranium will be consumed in this stage, so producing large energy. And in the end phase of that, then we can use thorium blanket, which will produce a fresh fuel uranium-233, which will go in the third stage. So this fuel once goes third stage, the thorium which we have abandoned available in India will be used, and the thorium will convert to U-233 in the closed fuel cycle, which will act as a fuel. So it will become a closed cycle, and we have a huge potential of 500 gigawatt electric for 500 years. So this is the energy security, and that is what Bhabha has planned that time. And after that, then next step was in 1954, DAE was established for required infrastructure for nuclear power program. So under this, whatever was like heavy water is required, fuel is required, reprocessing plants are required, for research and development various type of reactor, confidence building is required, physics calculation to be validated, design to be validated. So all various facilities was created. Okay, next slide. Based on this research program, actual confidence built up and people came forward from research reactor to power reactor. So before going ahead, let us see across what are the reactor under operation, construction, pre-project phases. Already CMD NPCL has brought out, he has told 400 gigawatt. In fact, 30 gigawatt is covered here. So operational is 8.8 gigawatt. Okay, in this one 2 BWR is already there, 2 VVR is operating, 21 PHWR is operating. Recently RAP7 is operating at full power. So around 25 reactors are operating. Under construction 4 VVR in advanced stage and 3 PHWR is also almost in advanced stage. Okay, one in advanced stage, but GHAVP is in the beginning stage only. This constitutes to 6.1 gigawatt, and then pre-project activity for 10 PHWR was initiated long back, and among that Kaiga 5-6 got FPC, so it will be switching over to construction state. Mahi Baswara is also going in advanced stage, so maybe permission will be granted and it will be in advanced stage. Others for Chutka and Gorakhpur 3-4 are still in the beginning phase. So with this, actual work has been initiated on 22.5. So we have to reach to 100 gigawatt. So 22.5 already in some shape and will come in by 2031 or 32, whatever is the plan. But one more next fleet mode 2 also approved and pre-project activity has been initiated. With this, it stays around 30 gigawatt. And as brought out, will come actual, okay, next slide I will come, please. Okay, before going ahead, let us just see how journey has started in India. First plant was taken BWR, so it is India's first nuclear power reactor, world's oldest operating reactor, that is the pride for us. It is also the soul of Indo-US nuclear deal. This one.
Slide, huh?
No, slide, indicator.
Pointer.
Pointer. Okay. So first nuclear power project was commenced at Tarapur, Maharashtra, taps 1-2 in 64, and the reactor type chosen was boiling water reactor. This figured, India figured in the nuclear map in world in 1965, just after 5 years, when these BWR were commissioned in Tarapur 1-2. Taps 1 and 2 were turnkey projects from General Electric USA, which were to be handed over to on completion to DA for operation and maintenance. Actually, it is not a part of our stage program, but what was the purpose and objective? Prove techno-economical viability of nuclear power in India, obtain experience in operation and maintenance. We have a operation and research experience for research reactors, but to generate this was thought a viable option. Then demonstrate technical viability of operating nuclear stations in the Indian grid. Actually, grid was of small size, and this was the big reactor, 200 megawatt. So sustaining the grid and collapsing the grid, what will be the behavior and what type of reactor should be sized. All the components of the power plant and nuclear fuel were imported, and the role of Indian industries was limited to construction, erection and service contracts. Actually, this is the old reactor, very old reactor, so health assessment was not up to that level, but over a period of time, based on the R&D available in India with various institutions, health assessment carried out with advanced technologies, plant life extended suitably, replacing the components and enhancing safety systems. In 2000, periodically it was enhanced, and therefore this reactor is working fine. And recently recirculation piping has been changed and it is running smoothly. This station has generated 100 billion units of clean energy, which we can see so much CO2 it has averted from the environment. It is also cheapest energy, around 2 rupees per unit. Next, please. Now PHWR, our main stage 1 reactor, in-house R&D expertise has been built over a period of time, and world record of 962 days operating record was there, world record by 2020. Now it is the second reactor. So as part of main thrust of developing PHWR design, RAPS consisting of 2 unit RAPS 1 and 2 was taken up as a Indo-joint Canadian venture in 1960 at Rawatwata, Rajasthan. Canada furnished nuclear design and supplied all the main equipment for the first unit. India retained responsibility for construction, installation and commissioning activities. So here we came in this picture in this one. For the second unit, manufacture of component was taken up in India and import component was reduced considerably. But Canada withdrew support from the plant in 1970 part due to Pokhran test, as we have seen in the morning. So therefore a technology denial phase started. So all the responsibility came to Indian engineers, and they carried out the remainder design, construction, commissioning work for the RAP second unit. And after successful operation of this, Madras Atomic Power Station, consisting of 2 units, MAPS 1 and MAPS 2, at Kalpakkam, started carrying out all facets of work on its own. But when going, actually safety is a dynamic thing, safety is evolving, things are changing as we have seen in the morning also. So therefore, notable design changes were incorporated in MAPS, improved reactor design were developed to keep abreast with evolutionary changes worldwide. To establish, actually now once we got the confidence, we have to multiply. So therefore, at various sites simultaneously we have to build. So therefore, it was felt necessary that site-specific environment data, site-specific environment and seismic criteria-based reactor external design should be evolved. And external design was evolved. In this reactor, improvement were incorporated to enhance reliability of operation, productivity. To common cause initiators should be ruled out, separate distribution of electric wire. All these things came in clear. And safety, like this really became a role model to begin with, and Narora, it was set up in Narora. So purpose was to reduce the cost and have better capacity factor. So the system, based on the operating feedback, whatever is required, some components were changed. Safety enhancement, suppression pool, double containment, they come in picture. Then after these 3 more units of 220 megawatt twin stations at Kakrapara, Kaiga and Rawatwara using indigenous technology was built up. After that, 2 more units at Kaiga and Rawatwata were repeated, which were completed in a record time of 5 years. So successful commissioning and subsequent operation of these units clearly demonstrated India's mastery in the technology involved and commercial activity. And Kaiga is the unit which has generated this. So till this point, actually we have got full maturity and confidence. Indian industry is also together. So therefore, all the issues which could be resolved effectively. This also established nuclear power as a safe, environmentally benign and economically viable source of power that offers energy security for the country. Now to realize, so 220 megawatt was running very fine, and records were performing, availability factor, capacity factor was also good. So now to realize economy of scale, design of 540 megawatt PHWR was developed, and construction of 2 such units was taken at Tarapur. Construction of these units again in a record timeline with international benchmark and later smooth commissioning and successful operation confirms maturity in design, development and construction and commissioning of nuclear power plant. So here we have completed 5 years, and here it is a like 540 megawatt, 2 loops were there. So core is also different, regulation is different. So lot of systems change were there. So this gave a good confidence to engineers, and therefore after that, next thought was that how to optimize cost of electricity production by exploiting economy of scale, and NPCL modified the design of this reactor to 7 megawatt capacity. Because same core configuration, only linear heat rate has to be increased to the level of 220 megawatt, which already we have a confidence. So therefore 700 megawatt was generated. These 3 units are being operated at present at Kakrapara, Rawatwata, as we have seen in the first slide. 4th unit is in advanced stage of commissioning, of commercialization. 2 units are being set up at Gorakhpur. Here, actually, there are some issues. Actually, it is not a smooth cakewalk as we have seen in the beginning. Every time there was incidents, there were surprises. So whatever design challenges was there, they are mostly solved and understood, examined and understood. But here in Gorakhpur, again, soil issues came. It's a soft soil. So this is again a first of a kind issue. So these, whenever issues comes, it takes time. But once we understand, because as told in the morning, there is no trick. We have to understand the things in detail. So things are being understood. It is taking time, yes. But we have to get confidence, and so that it should not reoccur in future. Future PHWR fleet mode, Kaiga 5-6, which got FPC permission. Mahi Baswara in advanced stage. It is expected soon. Gorakhpur, once this is resolved, it will also follow the same thing, and Chutka, it will be initiated. So after this, 10 more units got existing sites in fleet mode are being lined up as brought in the morning. So now, based on this journey, we can see that PHWR plants are running smoothly, and capacity and availability factor is very good. And that is the reason actually we are NPCL getting is good profit, because our overall efficiency is very good. Now in these reactor, life is limited, components are limited, and that is the beauty of PHWR, that these can be replaced. Fuel can be done on power fueling, we need not to shut down for fueling, and component can be replaced very easily. So therefore, upgradation and renovation is the key to extending the life on PP, and in many PHWR we have done the changes and we have restarted, which is running very smoothly. Aging management project is in place, involving inspection and plant replacement, cost of renovation versus cost of shutdown. So this is one point. Actually, what should be renovated, what should not be renovated. But if we shut down the plant for 2 years, 3 years, and some component fails later on, so it is a big challenge. Per day, what is the cost of generation? So therefore, it is optimal. Whatever component we feel there is a problem, we need to change that. In fact, original plan was NMAS coolant channel replacement with better material in short plant period, because it was known that this coolant channel will not go the full life of the plant. So it was known. So these were changed. But then later on it was seen in feeder thinning observed in Canadian reactor in 1955. Though we have not observed, but we have gone in depth what was the reason, what is the operating condition, chemistry condition, what is the material. So therefore we saw that our material has not degraded. But still decision was taken, let us change the feeder also. Because if after 5 years we have to change the problem. So that is what is the lesson learned, that we should go in detail what need to be changed based on the performance of the component, failure history, and we should change in one go. So appropriate measures taken in upgradation, renovation and modernization. Now besides this, sometimes unique failures happens, routine maintenance, special repair maintenance were taken up in mission mode. Repair of end shield, reps on end shield is one of the tasks. Introduction of spargen in maps 1, 2, because these are the old reactor, so material understanding at that time was not that good. So these known problems were there, but these were very well understood, and reactor were rerun again, which was a real challenge, but it ran smoothly for some years. This is also ran for a long time. Repair in end-shield Kaiga reactor, which was the latest reactor relatively, but again some problem came, so we understood. So from the failures, actually we have understood, from the experience, like for example, instrument relief valve, there were some failure. So in steam inner tube, there was some failure. Many components, there were failure. Major component like coolant channel was one of them. Trips were frequent. So all things were understood, studied in detail, and that has been reduced. And that is the thing that systematically our shutdown was yearly, then we have reduced to 2 years. And so we could achieve the 962 days record also. Now, after this PHWR confidence, then to have rapid extension of nuclear energy within stage 1 program, because PHWR, we are generating maximum whatever we can install, but additionally it is easy because these are the large size reactor. So it was thought that let us have VVR reactor from Russian cooperation. So 2 units are of 1000 megawatts are running in Kodankulam, 4 units are in construction stage, 2 are in very, very advanced stage of construction. Similarly, it is planned to install large size reactor through international cooperation. These plants are additionally to indigenous PHWR program of first stage. So discussion and negotiation are being held with EDF, France, for 6 units of 1600 megawatt at Ratnagiri site, which in the morning CMD has told 17,000, 16,000 and 11,000. So 17,000 is together. This constitutes the 54,000. Besides, one more fleet mode is expected in the future to meet the target of 54,000 gigawatt. Next please. Now this was the stage 1 with additionality of light water reactor. Now coming to stage 2 reactor, this is the fast breeder reactor program in the initial phase. Actually it is the initial phase. So here all teething troubles will come. We have to resolve, we have to understand, and we have to take control one by one. But it is a noting point here that for this itself in the beginning, 1965, for second step, plutonium reprocessing facility was inaugurated in 65. Critical facility research reactor utilizing plutonium fuel was developed at Jarlina in 1972 itself. To gain first-hand experience in fast reactor technology, FBTR was constructed commissioned in 1985 utilizing indigenous plutonium uranium mixed carbide fuel. It ran very smoothly and it has achieved a target burn-up of 1.5 lakh. This provides valuable design operational feedback besides high burn-up fuel, demonstrating breeding capability. So prototype fast breeder reactor was initiated in 2004 at Kalpakkam and is in advanced stage of commissioning. As I told, there are some issues and teething troubles, but it is understood one by one and it is resolved satisfactorily. This stage will have its importance till all depleted uranium from the first stage and converted plutonium is utilized. So therefore, it will take long time. Multiple reactor will come once we get confidence and maturity. So therefore multiplication will occur and this stage will go in a long way to generate 300 gigawatt energy for long time. Next please. Now stage what? Stage 3 reactors, full-fledged utilization of thorium in its R&D phase. So it is in R&D phase. But if we see in beginning itself, stage itself, as part of studies, U-233 fuel, a 30 kilowatt pool type research reactor Kamini was designed and built in Kalpakkam. Prior to this, a mock-up of the core of this reactor was built and made critical in April 1992. It was given the name Purnima 3. Kamini was made operational in 1996. This reactor is being extensively used as a neutron source for research applications such as neutron radiography of irradiated fuel. So therefore, research of this, what are the issues are being understood. Full-fledged stage 3 will take control after depletion, after stage 2 actually. So it is a sequential stage. After one stage, second stage, and thorium utilization will be full-fledged. But in between, based on this research, some thorium bundle has been used in PHWR itself. Uranium-233 has been produced and reprocessing. What are the challenges? So all being parallelly being done. So as we have seen, actually this reactor program will go together with the safety. It is not independent. With the experience, all things are clubbed together. Though a separate presentation after me is already there for safety, but I thought some points which will be relevant for this presentation, let me cover here. Also, Grover Saab also told fundamental safety objective of safety is protect people and environment of harmful effect of radioionization. But this fundamental safety objective has to be achieved without unduly limiting the operation of facilities, the conduct of activities that give rise to radiation. So to achieve fundamental safety objective in all stages of nuclear facilities, 10 safety principles have been formulated. But genesis of all this is that nuclear fuel should be cooled at all given times and radioactive fission product and minor activity are confined. And radiation care has to be taken. That is the essence. And these are the safety principles I will not cover here, but I will come prevention of accidents with the provision of defense in depth. This part I will cover, which is relevant for this presentation today. So here, actually safety is also evolved over a period of time. Initially we used to say we have a 4-layer of containment, one fuel is contained. So different place, common cause failure should be there, fail-safe design should be there, redundancy, diversity should be there. But how actually it should be understood in detail. So therefore, clarity has come in all the documents in IA and our ARB documents, and documents has been issued. So basically, purpose is that reduces the probability of an accident equivalent to a star falling on the earth. So actually we have to reduce the probability so that common man is not getting affected. So how to do that? So actually 5 levels has been generated. So level 1, 2, 3 was there from the beginning also. But the understanding and implication like fail-safe design, but how much fail-safe or process system, safety system were merged together. In RAPS 1 if we see, same is the shutdown system, it and linked with the process system. So that way clarity came one after another from generation to generation if we see. So level 1 was prevention of abnormal operation and failure. So essential means was conservative design and high quality in construction operation. So basically this is the key. I think next speaker will cover that. So quality should be there. Because in radiation environment we cannot change the component. For the industry actual lesson is that only, as on today like mobile, if there is a problem we'll change. If in the thermal plant turbine problem is there, we'll change the turbine. But here it become inaccessible. So nothing can be done. A special tool to be developed to repair that, which takes much longer time. Therefore, initial commissioning, construction, installation, commissioning, all this quality, reliability is to be understood and implemented very effectively. So here if normal operation is working fine, there is no problem at all. Actually we are fine. But if there is any deviation, that deviation should be detected. So system should be available to detect the deviation, and control of abnormal situation should be controlled within this level 2. For this, control and limiting and protection systems and surveillance features exist. So this layer is independent of this layer. So here independence of layer is the most important part. Now if things exceed to 3rd level, so here this is the accident, control of accidents and design basis. So these are accidents are within design basis. For that separate engineered safety features and accident procedures are there. So up to TMI, if we see a TMI accident happens in 1979. So lesson was learned and people were operating. But one lesson we learned from this event, that till that time they are in a category, if you do the major governing case, then things are understood and everything is controlled. But that was not the case. It was not a large loca, it was a small loca. In large loca, everything gets released together, ECCS comes, it flood together. So therefore, it is designed to show safe. But here it is a small thing. So therefore, things could not be mitigated. So lesson learned was there. This layer should be understood very well for all the pies, and any pies which can create different type cliff edge effect, which should be understood and implemented. Now after this, Chernobyl came. Here actually we were, severe accident we were addressing earlier for single failure, dual failure, for limited way. But Chernobyl gave a lesson that all design aspects should be covered, severe accident should be covered in design stage, in detail. And for that complementary measures and accident management procedures were there. But after that Fukushima, when it came, a next slide is there, I will cover on that. So that really made a challenge on this, that this layer is not one layer, actually it is multiple layer. This is design route. If design route is not available, then also, because that layer, tsunami layer was 15 meter and design was for 5 meter. So there may be something unexpected. So for uncertainty, how to account that, and that gave a lesson, and this layer was strengthened. And final level, if we go out, then how to control offset emergency measures for to avoid significant release consequences. Next please. So now evolution with experience, actually we have learned from each experience. In Indian context also, in all the plants we have seen various event, flooding event, SBO type of event, LOCA event, we have seen various events, we have seen minor trip operation events we have seen. So from that we have learned, but finally Chernobyl I have said, but here to have limitation time, I will cover the Fukushima aspect only. So after Fukushima, lesson learned from Fukushima accident, and outcome of the safety review post Fukushima utilized for safety enhancement of Indian NPP. As our CMD told in the morning, actually accident happened there, but all our program was delayed. This 700 megawatt which used to come in 2015 got delayed, because all these measures should be understood and implemented in the plant. Construction started already, but then we have to implement. And the focus was unavailability of designed power supplies, unavailability of designed water routes. Because designed routes were available, if everything is okay, so no issue. It will control and manage the situation for severe accident. So unavailability and extreme events and margin assessment. So safety enhancement were identified, implemented in phases, short term, medium term, long term, because plants were operating. So anything can happen that time itself. So short term measures identified which can be implemented quickly. Then medium term measures, and finally long term measures. Long term measures, if design routes is not there, so then other arrangements to keep, including containment, plant in safe conditions, were implemented. Now one slide or more, ensured as multiple levels. Actually the beauty that to have shared safety, we have to have multiple levels and all should be independent. So this we have to see very thoroughly. In fact, for safety we have deterministic approach, that various type of pies, for each pie what are the consequences, how it should be mitigated. Then we have a probabilistic safety assessment. The area or uncertainty not covered here are captured here. But again it is not 100%. So therefore failure can happen. Therefore various levels are there, procedures are there. So we have to adhere to that, and we have to intercept in between. And how we are doing this? So multiple layer of safety reviews are there. Station operating review committee at the station itself is there. And other station people incorporate review station independently the performance of the plant. Then in head office, any document going to ARB, NPCSRC reviews that. Similarly, international 1O review and IEA review also taken in the task mode. So plants are reviewed, multiple layers are there. Then this review document for implementation goes to ARB. There also independent multi-tier safety reviews are there. The detailed process of authorization for new plants, as well as periodic safety review of operating unit by Atomic Energy Regulatory Board, add value and maintain vigil on all aspects of safety. Safety encompasses all stages of nuclear power plant execution from siting. Actually it starts from siting. Then design, construction, testing, commissioning. So all aspects are very important. If something is missed here, nothing can be done later on. In design, if something missed, nothing can be done. Retrofitting cannot be achieved with that level, what can be done in the design stage itself, and commissioning and operation. Very important for all layers to be independent, because nuclear accidents are not merely an accident, it is a disaster. One of the presentation as I was hearing, in fact I was surprised, so they told so many people get death in the accidents, in the car accident, train accident, plane accident. But this is not the case here. It is disaster. Actually, Fukushima, nobody died because of this, but because of disaster, people have to evacuate. So losses were there because of that. So this is the lesson for this, that because of, to prevent that, we have to maintain carefully. Release to environment have been a small fraction of limit prescribed by the ERB. PHW are the safest with respect to severe accident. Actually, the PHW design is such that water is around fuel. Multiple layers are there for water. So they are inherently for severe accident. This is one of the good point in the PHWR. Importance of R&D in nuclear energy. Actually, India has acquired expertise in entire range of nuclear fuel cycle activities. And this was the thrust from the beginning, as we have seen: research reactor, multiple facilities, experimental facilities, theoretical understanding, experimental understanding, validation of the things has been brought out. So in fact, due to technology denial after 74, over a period of time, it has become much stronger. So in fact, it has become an asset that when technology was not available, we have to develop our own. RAPS 2 starting got delayed, but then we have understood the things and industry became stronger. Industry could generate the component here. So that was the asset for us. R&D activities pertain to wide range of material testing, because material what is to be used, if like some material are there, they get irradiated and become much more inaccessible. So that specification what is provided in the tech spec should be honored rigorously. Conceptual design was evolved, pilot studies, design verification, validation of data. This validation, for the name, we cannot say, well, we are confident on validation. Actually, we have to do, otherwise some new event will happen, and that time it will be in difficult situation. System performance, various kind of first of a kind activities. After Fukushima, various first of a kind features has been installed. Based on this R&D experience, we could put in a much less cost. Actually, that is the reason PHWR cost is the lowest in the world. And our reactor, if we put in India, is still the cheapest. Any reactor, whatever we put in India. So, but because it has so many safety layers, rigorous things are there, so cost anyway is comparable, at least if we are far away from the coal mines. I have some slide on the tariff, I will show that. Then besides this in-house R&D, international collaboration through various agencies wherever possible is extended, namely IAEA, WANO, COG, ITER, participation, OECD, NEA. So wherever opportunities are there, our people from India are participating, they are getting confidence, they are demonstrating their capability, and therefore we have a good relation in all these. Capability in all aspects of R&D, including this now, in safety design, design, engineering design was demonstrated in the country. So that confidence has built up now. A strong R&D base is one of the important assets in the nuclear field. Any abnormal events have happened during the plant life is examined in detail. Reasons are well understood before implementing corrective measures. This is one of the major strengths leading to sustained operation, long-term operation. Because we have removed all the culprits, and so therefore long-term sustained operation, giving to availability and capacity factor very high and leading to the profit. And scaling up of PHWR capacity from 220, 540 and 7 megawatt, which brought indigenous nuclear power program to a maturity. Now some slides on the tariff and project cost. So if we see, actually Tarapur unit when set up, it was 4 paisa per unit. So it was very low. But over a period of time, because so many renovation, modernization has done, that cost has become capitalized and cost has gone to 1.92. These data are 23-24 data. So relative cost, if we see Tarapur 192 paisa, Madras 261, Rajasthan 334, Narora, so of comparable. But latest units, Tarapur 290, Kaiga 348, Kodankulam 4 rupees, Kakrapara, which is latest, we were selling at 450. Average tariff came to 383. But if new reactor we see, it is 5 rupees 25 paisa for RAP 7. So cost, because capital cost is increasing, if we see capital cost here, earlier reactor at that time The prevailing cost at that time, it was 5 crore, 7 crore, 10 crore per megawatt. Now Kakrapara 3, 4, when it started, it was 16 crore or so. So after delay also it is in this range. But Kaiga 5, 6, which is the next FPC has been granted, expected cost will be 20 crore per megawatt. And future 7 megawatt, which got pre-project activity approval, is expected to be 25 crore per megawatt. Next, please. I have got some slides from WNA to get a breakup for the various costs, capital costs. So breakdown of activity for PWR, I could get that. Design, architecture, engineering cost, licensing cost is 5%. Project engineering, procurement and construction cost is 7%. Construction and installation cost, which is a major part, for nuclear island 28%, conventional 15%, balance of light 18%. So this is the major part. Site development, civil works, it depends upon what is the type of site and conditions, so it may vary. Transportation 2%, commissioning, and this can depend upon if we have marginal procurement contract, so it will go there. Commissioning and first fuel loading 5% because it is one time fuel loading in the beginning, total 100%. Next slide. If we see capital cost breakdown of labor, goods and material of PWR, different way of showing. Equipment is 12% for steam supply system, electrical 12%, mechanical equipment 16%, instrument is 8%. So this is the major cost. Construction material 12%, labor is 25%, project management 10% is this way, fuel load 3%, it becomes 100%. Next. Now the key achievements, if I summarize that, TAPS 1-2 being the oldest station in the world are operating satisfactorily with renovation and modernization, meeting safety standard and producing cheapest electricity in the country. In fact, the safety feature put in this 1-2 small reactor are very good features, and therefore we are confident it will run smoothly, and piping has been changed. So let us hope it will run very smoothly and generate the cheapest power. Performance Indian nuclear power reactor in the terms of safety has been excellent with over 600 reactor years of safe, accident free operation. Each experienced national and international is reviewed and safety provision revisited and improved upon if required. That is meticulously built in our culture. Attained one high time longest operating reactor piece of world record. Continuous long term operation giving rise to large capacity and availability factor. Very low level of release to environment. In fact, we see more than 1 year, lot of reactors has continuously operating more than one reactors. Kodarikullam reactor also continuously operating from beginning. So this same thing in Tarapur also. So very low level of releases to the environment. So take away for the industry, actually proven PHWR design is ready and industry can come forward and implement them to reduce India's carbon footprint. Thank you very much.
Thank you, Mukesh ji. You accepted my request and finished in 45 minutes. Thank you very much. One or two questions. Otherwise, Mukesh ji will be available during lunch time also. Yes.
Shri from Toronto. Sir, I have a very quick question. If you look at the CANDU reactors, with every refurbishment, they have operated. For example, Darlington, which is the latest CANDU reactor, when it was originally built, it was 800 and some megawatts. Now it's 900 and some megawatts. So are the Indian PHWRs also looking at that upgrades? Because when private companies come in, they would want to get the maximum out of that infrastructure. That is one question that comes to mind, if you can shine some light on it.
Actually, see, after 220 megawatt, we have scaled to 540 megawatt. So one thought was there, let us operate 540 megawatt, because whenever we make any change, when we make a change from 580 to 7 megawatt, we thought it is a very small change, but it got delayed and so many delays. So now people are confident, and one thought of school is there, let us not modify the design, run the reactor of the same kind. Maybe after we will see later on. So therefore, economy of scale, because here calendar size has to be changed. 540 to 7 megawatt, same calendar size, same number of channel. So at least that part is same. Okay, whatever minor changes we have done, so that has impacted the delay. So therefore, thought is that let us not change the design and operate 7 megawatt in a series, and we'll see later on. That Darlington 900, that is one option we can think for that, but for the time being, I think there is no thinking on that.
Thank you, Mukesh ji. Is there any question? No.
One very quick question, sir. When you go from PHWRs, which are so cost effective, the moment you talk about foreign players coming in, cost of producing power will not be the same. It will be significantly more. How does the Indian program plan to address it?
See, actual power is to be, we need it for the people. People have to pay. So they will pay whatever cheapest is available. So therefore, actually industry has to come in a manner so that our localization should happen. Why these are costly? Actually, if localization increase, I understand negotiations are happening here, discussions are having. All this component, if manufactured in India, maybe cost will be reduced. That is the only way, because it has to remain cheap so that people should.
Yes.
The tariffs which showed, can you just throw some light? What are the recent cost of funds which are considered for such tariffs?
Okay, can you mean so that?
Say for Kaiga and all, what is the cost of funds we are considering?
Last project tariff. This one. Yeah. See this Kaiga 5.6, which we recently got FPC, we are expecting 20 crore per megawatt.
Yeah.
Okay.
So, in that calculation.
Tariff.
Yeah, tariff. What is the cost of funds which
Okay.
When because price
Okay.
would like to
Okay.
Yeah, as Mr. Bhardwaj explained, the numbers will be discussed in tomorrow's programs. I thank you, Mukesh ji, and I'm very happy that earlier two speakers managed to save the time for the session.